So if you have any questions about anything, or you need to plan something, I'm here all night. So I'm going to read some sponsors and then introduce our lovely speaker. So we've got Capture Technology, Improving is what we do, Texas A&M Cybersecurity, Innovation Underground, HTRI, ISSA, we've got T-Star, Electronic Systems, Engineering Technology, and then of course Red Cyber Theater, which is this lovely building that we're in. So give me help me welcome our presenter, Kimberly.
Wearable Technology for monitoring cardiac and diabetes biomarkers. I bet every single one of you knows someone who has been diagnosed with diabetes or cardiovascular disease. In particular, every 30 seconds in the United States, there will be someone who is diagnosed with diabetes and someone else who suffers a coronary event. When we consider underrepresented and underserved populations, there's a disproportionate amount that have these chronic illnesses. So when compared to white non-Hispanic communities, African American adults have 72% more likelihood to be diabetic. Latino and Hispanic adults have 63% more likelihood to be diabetic. In terms of cardiovascular disease, an African American adult is 32% more likely to die from the disease. And a Latino Hispanic is 83% more likely to be obese, where obesity is a precursor, typically for development of diabetes and cardiovascular disease. These chronic illnesses rank number 1 and number 8 killer in both America and globally. What are we doing about it? How are we helping our patients to better monitor their situation? Well, currently, to monitor diabetes, we use blood glucose monitors. That's where we prick our finger, we take a small amount of blood, we put it on a test paper strip, and we feed it into a reader. We also have continuous glucose monitors, which are minimally invasive, wearable, that you can put on the back of your arm typically, that will measure your glucose levels continuously. Both of these are invasive approaches. Both of them do not predict if you're going to have a hypoglycemic or low blood sugar event. In terms of cardiovascular disease, hypertension happens to be the leading risk factor. How do we measure hypertension? Well, we use a blood pressure cuff. Every single one of you probably used a blood pressure cuff at some point in your life. They're not the best measurement capabilities. They're not the most enjoyable either. And for those of you that have hypertension, or for subjects that do have hypertension, most likely they'll measure their blood pressure once a day, and at best, once an hour. But you're missing a lot of measurements in between. You don't know how their blood pressure is fluctuating throughout the day. You don't know if the medications that have been provided they are adhering to. And you don't necessarily know if the medications and treatment plans that are being given are good enough. The only continuous blood pressure monitoring device is an arterial catheter that's usually reserved for very sick patients in an ICU, and it's a highly invasive approach. So currently, there is no way to continuously monitor blood pressure. This is where wearable technology comes in. So let's talk about the scope of wearable technology. It comes in all shapes and sizes. You have aids like eyewear, earbuds, smartwatches, fitness trackers, patches, shoes. You measure all types of signals such as heart rate, respiration rate. It can tell you if you're stressed. It can tell you if you slept well. It can tell you about your biomechanics. But in particular, with the advancements in AI machine learning, it can also help you monitor blood pressure and diabetes. And that'll be the focus of today's talk. So to go through some of the current commercial available wearables, many of you probably have some form of smartwatch. Things like Apple, Fitbit, Garmin. And so there's also other wrist products such as the Impatico, which is a research-grade wearable. In terms of smart garments, you have Medtronic's Zephyr line. In terms of finger systems, you have the Oura Ring or a pulse oximeter. In terms of chest devices, you have the Zephyr Bio harness or the BioTel chest patch. What do all these have in common? Well, they can measure physiological parameters. What they don't have in common is FDA approval. Some of them are, but not all of them. Some of them have FDA cleared algorithms on board, but most of them do not meet the criteria to be considered a medical monitoring or diagnostic tool. So that's where we come in. Our goal is to improve the current technology so that we can reach medical accuracy. The way we do that is we try to work towards compensating for things like skin tone. In particular, smartwatches that utilize optics-based approaches don't always compensate for skin tone variations. We also look at trying to compensate for body mass index changes along with motion. Motion is the #1 artifact developer for wearables, all wearables of any kind. Removing motion artifacts is a very difficult challenge. And without the ability to do that, you will not be able to create a wearable technology that can be deployed continuously both day and night, inside and outside of the clinic. So by improving the current technology, we also hope to push the limits. There were words there. What they said was we were trying to push the limits of our wearable technology, and in particular, we want to measure blood pressure continuously. And we also want to non-invasively predict if someone is going to have a hypoglycemic or low blood sugar event. So how are we doing this? We're taking two approaches. One, we created an upper arm wearable, and the other, we created a wrist-based wearable. The upper arm wearable is to predict a hypoglycemic event, and the wrist is to monitor blood pressure. With the modalities on board both of these devices, you can also measure metrics such as blood oxygenation, heart rate variability, respiration rate, temperature, among others. To go further into those modalities, our devices contain metrics such as photoplethysmography, bioimpedance, electrocardiography, skin temperature, and inertial measure impedance. I'm going to talk briefly about bioimpedance or BioZ and photoplethysmography or PPG. So bioimpedance is a modality where we inject a small amount of current, an oscillating current, and we measure the voltage change. We're able to calibrate that to impedance response. So what happens as our heart beats and pushes blood throughout our vasculature, the blood will push through our arteries, expanding them, and that expansion will then push along the cells outside the artery. Pushing on these cells will cause them to deform and cause impedance change. So what we're able to measure is the cyclical signal at the frequency of the cardiac cycle. We're also able to measure a similar cyclical signal using photoplethysmography or PPG. This is an optics-based approach. This is what is inside most smartwatches and fitness trackers. So what happens is we have an LED that shines into the tissue. Within the tissue, we have blood that will absorb the light. So as your heart beats, when the blood volume changes, you will get a cyclical signal, again, at the frequency of the cardiac cycle. Both of these modalities, along with electrocardiography, allow you to measure heart rate and heart rate variability, among other things. So this leads me into our first device. We're going to talk about a blood pressure monitoring system. So studies have shown that for every 20 millimeters of mercury drop in systolic blood pressure will actually reduce the probability of death by heart attack or stroke by 50% in all age groups. So what this tells us is that there is a need for the ability to be able to continuously monitor someone's blood pressure, especially if they are hypertensive. So the way that we go about creating this particular system is by combining both photoplethysmography and bioimpedance. And we do this in an approach where we want to measure 2 channels of PVG and 2 channels of bioimpedance. And so what you see on our green PCB in the middle is at the very end of the PVG sensor, and in the middle there are 6 electrodes. The outer 2 most electrodes are injecting our oscillating current, and the inner 4 are measuring our voltage change. So what this gives us now is 2 channels of PPG and 2 channels of bioimpedance. You may ask why. What we're trying to measure is something called pulse transit time. And as the name suggests, we're trying to understand how long does it take for a pulse to move from point A to point E. In particular, it's been shown that by utilizing pulse transit time, you can correlate that metric back to blood pressure. So our device is placed along the radial artery, and we're hoping to measure the pulses that move throughout. And for the rest of this talk, the PPG signals that we measured came from a red wavelength sensor. The bioimpedance signals that we measured, we utilized an injection frequency of 17 kilohertz and a current of about 900 microamps. So because our subjects were very healthy, young individuals, we needed to figure out a way to change their blood pressure. We wanted to be able to see if we could measure hypertension. So we did that by asking them to do minimal exercise using leg press. So we measured signals on 3 females and 3 males, and we used the press, which is our reference continuous blood pressure monitor. It's a cuff-based approach. It's a small cuff on your finger that inflates and deflates and continuously tell your blood pressure. To elevate our subject's blood pressure, we asked them to use a leg press machine, where we wanted them to work at 3 different levels, each level getting progressively harder, and each level increasing your blood pressure. So now we have a range of data going from normotensive or normal blood pressure to hypertensive and high blood pressure. And then lastly, we utilized our system to measure continuous 2-channel PPG and 2-channel bioimpedance at the same flow rate of 1 kilohertz. Before we were able to extrapolate what we believed the blood pressure was, we had to do some data pre-processing. The way we did this is we combined signals from all 4 channels, remember 2 channels of PPG and 2 channels of bioimpedance, and we did some filtering. We used bandpass filters to remove any of the DC offset and baseline monitor, along with any of the high frequency noise. To extrapolate each of the beats within these signals, we used an open source toolkit called NeuroKit 2, and that allowed us to find the troughs in our signal of the foot. We were then able to separate these individual pulses, and we averaged 5 of them together with a 1 pulse overlap. From these averages, we were able to create a reference pulse. And from there, we normalized both our average pulses and our reference pulse. And we correlated the two. Because when we did that, we wanted to create an ability to reject any pulses that did not meet our standards. So we created a signal quality index. And so if our pulse did not meet our standard, we rejected it. Most of the time, the reason we rejected it is due to motion. So from the accepted pulses, we then stack them. These are normalized pulses. We have 1 channel, 100 samples, by a number of pulses. And that was done for each of the individual modalities in each of the channels. This was then concatenated into a 2-dimensional array, 4 by 100, where each row represented 1 channel of our signal. This was the input into our model. So we worked with a baseline random forest model where we took these two-dimensional arrays and we fed them in. What we asked ourselves was, do we really need all 4 channels of signals? Or is there a lot of redundancy here? Could we get away with just using one modality? Could we get away with just using one channel in each modality? So when we did that, we found, as you can see in the highlighted red box, that when you put in just one modality, one channel, you have a higher mean absolute error than when you put in all 4 channels of data. So what that told us was by having the redundancy of 2 channels along with 2 separate modalities, we got a better accuracy. So looking at our predicted curve, as you can see, we were able to predict systolic and diastolic blood pressure with some form of accuracy. And you can also see the difference in our residual curve as well. To give some statistics to this, we were able to calculate the systolic blood pressure with a mean absolute error of 1.9 plus or minus 3 millimeters of mercury, and the diastolic blood pressure of 1.5 plus or minus 2.2 millimeters of mercury. One of the issues with this, though, as you can already tell, we only used 6 subjects. It's a very small data set. We also used normotensive subjects, so we have even looked at hypotensive or hypertensive, both low and high blood pressure subjects. So the next stage is to do just that, to include these different varieties of subjects to see if our algorithms hold true. The other part is because we use this dual modality approach, and we're using both an electrical and an optical approach, we want to be able to try to increase the number of pulses that we accept and decrease the number of pulses we reject by being able to remove motion artifacts and reconstruct the original pulses. Now I'm going to flip over to the diabetes portion of this talk. So the last system was a multimodal approach, and this next one will be as well. But in particular, this one is trying to target the ability to predict a hypoglycemic or low blood glucose measurement 30 minutes before it happens. For those that have or go into hypoglycemia, it can cause you to feel very dizzy or fatigued or pass out. Now imagine if you're behind the wheel of a car and you have one of these events. Imagine if you're working heavy machinery. It's not ideal. So for those who have poorly controlled blood glucose, it can lead into some serious complications, including kidney failure, heart disease, amputation, or stroke. You may say, well, you have a continuous glucose monitor now, so why not just monitor your glucose that way? Well, in the hypoglycemic range, these monitors aren't as accurate as they are in a euglycemic range or a normal glycemic range. So therefore, there's still a need for a technique, preferably a non-invasive technique, to allow us to predict if someone is going to be hypoglycemic before they get behind the wheel of that car. So our collaborators in the Department of Computer Science and Engineering work to create preliminary algorithms to do just that, to predict a hypoglycemic event from non-invasive measured signals, while we were working on creating wearables, which we'll talk about in a minute. So these algorithms that we started to create were based off the use of commercial off-the-shelf devices. In particular, we deployed the Zephyr bioharness and the Empatic wrist strap. The Zephyr bioharness allowed us to measure electrocardiograms, and the Empatica allowed us to measure PPG among other signals. We deployed these on 10 healthy subjects with type 1 diabetes. We were able to create a preliminary algorithm that allowed us to predict a hypoglycemic event. In particular, what we wanted to look for here was for the data set that we were using, we wanted to see if we needed to look at beat-to-beat morphology, if we needed to look at interbeat intervals, or if we could simply just use heart rate variability features to help us to predict a hypoglycemic event. And so what we did is we combined a convolutional neural network that looked at the ECG beat morphology, a long short-term memory or LSTM network that helped us to look through the interbeat interval information, and aggregated that with our 16 statistical heart rate variability features that we extracted using the open source NeuralKit 2 toolkit. And what we found is that when you create an algorithm that looks at each of these feature sets individually, it is not as accurate as it would be by combining all of these feature sets. So what this tells us and what this sets us up for is for when we are able to create a system that can aggregate multiple sensors with multiple feature sets, we'll most likely have a higher ability to predict a hypoglycemic event. So, as we were creating these preliminary algorithms, we started to work on development of our upper arm wearable. Why the upper arm, you might ask? Most wearables are on the wrist. When we started to look through our empathic data, we noticed that a lot of it was unusable because of motion artifacts during the daytime. And so it's been shown that an upper arm wearable is actually not as affected by motion as a wrist-based wearable. So that's number one. Number two is a lot of our algorithms are dependent on being able to extract ECG. Well, when you have a wearable on one side of your body, you're not going to be able to extract the full waveform. You can extract something called single-sided ECG. And so we found that by creating an upper arm-based wearable, we're able to measure the most optimal single-sided ECG signal. The further down the arm you go, closer to the wrist, the smaller the signal gets, and therefore the lower quality it is. So our goal here was to combine a multimodal approach. We integrated sensors like PPG, bioimpedance, single-sided ECG, skin temperature, and it also integrated an inertial measurement unit containing a 3-axis accelerometer and a 3-axis gyroscope. The inertial measurement unit was there to provide us with that contextual awareness, to tell us, is the patient sleeping, are they standing, are they walking, are they running? And that later will help us to work on our motion reduction algorithms. And so particularly, we spent a lot of time figuring out where we place all these sensors, where we place all the electrodes needed for these sensors. And so what we found was that single-sided ECG electrodes, as mentioned before, should be placed as high up on the arm as possible for the best signal. And PPG, bioimpedance, and temperature sensors should be placed on the inner part of the arm near the brachial artery for optimal signal acquisition. So to give an example of the signals we were able to measure, what you see here is the accelerometer and gyroscope, which are flat lines because the subject was sedentary. You see the single-sided ECG, 3-wavelength PPG, and bioimpedance. All three of these allow us to measure things like heart rate and heart rate variability. So having this redundancy allows us to, one, cross-correlate and check between the three to make sure that we are pulling out accurate metrics. Two, also allows us to mitigate things like skin tone. Having two electrical approaches no longer affected by skin tone allows us to have a more accurate device. And so the next stage with this project is we just deployed our upper arm wearables along with our commercial off-the-shelf sensors. And we hope to collect a very rich data set that allows us to then predict hypoglycemia events, and hopefully 30 minutes before they happen. The second part of this study is to look at creating motion reduction algorithms. So in particular, when you look at the picture on the left, there's a sedentary signal. Someone who's when you look at the picture on the right, there's someone walking. There's a really big difference between the two. What you notice is in the accelerometer and gyroscope, there's an oscillating cyclical signal, most likely due to the person swinging their arms. And same thing you see in the single-sided ECG, PPG, and bioimpedance signal. You see an oscillating signal. So our hope is that we can create algorithms that can reject the common mode noise seen in all these signals, and also adaptive filters that can then reconstruct those signals to allow us to then accept more data during the daytime, which is more affected by motion, so we can have a larger and richer data set to work with to predict hypoglycemia events. So in conclusion, what we talked about today was the ability for wearable technology to allow us to measure blood pressure and hypoglycemia. We're working on trying to improve the current technology by utilizing multimodal approaches that can help us compensate for motion, body mass index, and skin tone. This then lets us push the limits of wearables so that we can create a continuous, cuffless blood pressure monitoring system to help decrease the prevalence of hypertension. And we can also create a non-invasive technique to predict a hypoglycemic event 30 minutes before it happens. And I'd like to acknowledge my faculty advisors, along with my lab, in particular graduate student Dustin McMurray, along with research engineer Richard Horner from TEAS, and the funding resources. Without all of this, none of this work would have been possible. And thank you for your time.
Any questions? I have a silly question. We have a question. Yeah, can I be in your next study? Not that bad.
I love that.
Learn about a hypo 30 minutes beforehand. Yes, I can.
Perfect.
You know, I was wondering if heart rate comes into play on the blood pressure measurement side, and if so, how can it determine to incorporate it into the data analysis or exclude it?
That's a great question. So it does. That's actually what we noticed. Our first models were based off of more of a feature engineering approach. So we looked at features that were in the time domain and were highly influenced by heart rate. We noticed that we were getting a high correlation between heart rate and blood pressure. So what we ended up doing was we extracted, or I guess excluded that by normalizing the waveforms. So instead of having them, for example, having 200 points for a certain heart rate and 100 points for another, we then normalize the number of samples to 100. So that way you're no longer looking at heart rate as a feature. And instead you're just focusing on the waveform quality to measure blood pressure.
Thank you.
For your blood pressure, you mentioned that all of your, besides there being only 6 studies or study participants, they were all like healthy. You also mentioned that is there a plan then for studying people who have like hypertension and everything?
Yeah, so right now we want to, I guess, iron out our preliminary algorithms, and the hope is to start recruiting hypotensive and hypertensive subjects as well. And then also, we hope to deploy a system that can be used in the real world and not in our laboratory, so we can start predicting signals outside the lab as well.
So you went from the wrist to the upper arm. I guess I wonder why not a necklace or a headband?
I like those approaches, but I don't think they'll be adoptable. Most people with their very smart garments now or smart wearables is on the wrist. Take your Apple Watches, your Fitbits. So in terms of people adopting them for the head and for the neck, I don't think they would be adoptable, not to mention for some of these modalities it's very difficult to measure on the head or the neck.
So 2 questions. First of all, there's been an increase in people with POTS. I don't know if you know what that. It's, I'm going to butcher the word, but it's osteo something tractio syndrome or something. I personally never heard of it 2 years ago, but I've had 3 close friends of mine discover they had it recently, and that wearable for the blood pressure could be very useful. So have you thought about considering people with POTS to be part of your study or targeting that segment?
I think I would have to do a little bit more understanding and research into what exactly POTS is, because as you can tell, I didn't 100% know. So, depending on how useful it is, I think for now we're focusing on subjects who don't have other illnesses, so that we can kind of iron out the preliminary algorithms, so I do think we can then eventually include specific subjects.
From my understanding, POTS is people that deal with sudden changes in blood pressure, so they need that constant monitoring of their blood pressure.